Professor of the University Libre de Bruxelles. Thomas did his PhD with Nicholas in Brussels, and he worked in the famous oscillator, which is a prototypical model for autocatalytic reactions. And he started in the chemistry department. Then he moved to the US as a postdoc at our applied math department. And he stayed for 13 years in the US in Northwestern University, and then he came back to Europe, went back to Brussels, and he has worked in a lot of topics. For example, he started with dissipative structures, Turing patterns, and Turing patterns in morphogenesis. That's the area he works. Often also he worked in propagating wave in reaction diffusion systems. He worked in, he started to work also with Baum-Mandel on optical instability, dynamics of nonlinear cavities, and so on. He worked on imperfect bifurcations, dynamics instability, and dynamics in synchronization in couple oscillators. And also he has done a lot of work in lasers, nonlinear dynamics of lasers, including at the beginning laser insaturated absorbers, then semiconductor lasers and crafty lasers, and also some work on pixels. And he also worked more recently in delay systems. Thomas has over 200 publications, and he has published 2 books. One with Pierre Boyer, who passed away a couple of years ago, on laser dynamics, and one on applied differential equation. Applied differential delay equation. And after publishing this so many publications, he has over 33,700 citations. And well, today Thomas is going to talk about this square wave laser dynamics in photonic systems, which is square wave arises in this delay system, and so this is one of the biggest experts.
Well, thank you very much, Ferre, and thank you for this invitation to this place. I have a lot of friends here. It's always a pleasure to come here and interact with the activities of the group here. You know why I put a picture of Brussels. I said this 2 years ago. It's because of Claudio. Claudio, in every this presentation, has a picture of Mallorca. Right? So I said, you know, I should also put a picture. So this is a topic that is old and also new, and I will try to show you why. I'm going to try to be not technical, so I'm going to assume that you don't know what a delay equation is, okay? And I will just go to the facts. So if you don't know what's a delay equation, this is a scalar equation where the state variable x, or the growth of the state variable x, depend on its present state, but also on its value at the time in the past, at tau in the past. Okay? And this is called a delay-differential equation. Now, why we're interested in square wave in application? Well, first of all, we can control the period of a square wave by a single external delayed feedback. Changing the delay, change the period. And I just want to mention that this is in the framework of J.Tidus, where she explored what you can do with 2 delays. And then actually you have much more flexibility to tune the period of the square wave. You can generate fast oscillation with a square wave. And maybe more interesting for application, you can have some new waveform, which is an alternative to what we used to see, which is nearly harmonic oscillations. So here is the presentation. I will give you an idea about the history, a quick overview of the history of square wave in optics and in general, in particular when you have a large delay tau. And there are the two topics that are currently explored by two students in Brussels. One is a two-mode optical feedback problem, where we're dealing with 2 tau periodic square wave. And another problem is an electro-optic delay oscillator problem, where we're dealing with a tau periodic square wave. A quick introduction about the history of square waves. Square wave appeared in optics in the end of the 80s when researchers, laser researchers, were interested to prove that chaos can appear also in optics. And Ketuda Ikeda proposed to a device which has a long feedback delay due to a longer fiber, 7 kilometers. And later on, this was then explored experimentally by Gibbs and his co-workers. So we talk about the early 80s. The model that Ikeda and co-workers were trying to explore were scalar equations of this form, okay, where f is a nonlinear function. Never mind what the function was, they are dealing with this particular problem. The first thing you should do, especially when you're interested in a very large delay, tau, is to change the time variable in terms of t divided by tau. And then in terms of the new time variable, delay is now fixed quantity 1, but appear here as a coefficient like 1 over tau. So when we say large delay, it means small epsilon. This gives you a numerical example of the solution of this scalar equation when you have here a function with a cubic nonlinearity. And typically, you can see some square wave solution. So we have fixed plateaus separated by quick changes between the plateaus. And the period is more or less close to 2. So 2 times the fixed delay 1.
Yes, no, shouldn't be in the denominator, in the left-hand side?
No. Delay large. Okay. This is not the same tau, t, right? Mm-hmm. I changed t to s divided t divided by tau, and then I renamed that s to be t. Mm-hmm. And then you have these steps. Now, in the early 80s and 90s, there has been a lot of mathematical interest for those kind of equations. Okay, in particular by Jack Hale and his co-workers. Okay, Nussbaum, Manet-Paré, they all have contributed on the connection between this problem here and the map that you get when epsilon goes to 0. Okay, so if you have epsilon equal to 0, you have here a functional relation between x and xt minus 1. And if you name x to be xn plus 1, this xt minus 1 becomes x or n, we have a map. So those people have studied and proved how we can connect this particular problem to this particular problem. For us, this is important because this is much easily explored than the differential equations. And what the fixed point of this map provide us are the value of the plateau of the square wave. Okay? You may have more complicated fixed point. Here we talk about the fixed point of 2. So we have those 2 plateaus, but you can have high order, square wave. But this is the one I like to concentrate. Okay? We can also see that they are nearly symmetric in the sense that the length of the plateau are identical, close to 1. So that's what I call symmetric, and I will come to that a bit later. Now, it's interesting to see that even if Ikeda has suggested that a scalar equation can produce square wave. The experimental setup that provide quantitative comparison between, let's say, the solution of this differential equation, or even better, the map and the experiment, came only in 2001. Okay. Before that, Ikeda made so many approximations to get the scalar equation that it was impossible to hope for a quantitative comparison. Now, this was done in 2001. This is the typical experiment using this particular model. So this is the experiment. We have two Hopf bifurcation, and here we have the onset of a chaotic output. Okay? So I mark those 3 points. What the oscilloscope is tracing is the extrema of the oscillations. Here we have many extrema. Here we have a maximum and a minimum, typical of the Hopf bifurcation branch. Here I explore the solution of the map, and from the map I can identify a Hopf bifurcation point and the onset of chaos. This is a numerical bifurcation diagram just by iterating the map. Okay. So you can see that there are actually extremely good agreement between the experimental value and the map value. Okay. But in addition, if you are running back and forth the bifurcation diagram numerically, you see that there is another branch of solution here that Laurent didn't detect it because he only went forward. Now here I come to the pertinent questions. Okay, so we have the scalar equation as a reference problem. The delay is large, that provide an epsilon. We know that if we kill the epsilon term, we have a map that is very useful. This is a typical periodic solution of the differential equation. I call them symmetric because the length of the plateau are almost identical. And here the question I'm raising. Can we have a symmetric square wave of PO2, meaning that the length of the plateau are completely different? Okay? Still, you have a two periodic solution. Okay? So we maintain that periodicity, but the duty cycle here, well, from the maximum plateau, minimum plateau are different. So this is a question I raised. And why do we have always PO2? Why not have PO1? Okay. Now you can show that this solution here may exist as transient, but they're never stable solution of the scalar equation. And that's introduced me the first problem that is explored by Gaëtan Friard, who just started his PhD. This was his master's thesis work. So he actually explored a relatively old problem. We have an edge-limiting laser, we have a Faraday rotator, and we have an external mirror. So the main polarization here is rotated by 45 degrees, go to the mirror, get another 45-degree rotation, and hit the laser in the orthogonal polarizations. So this adventure of looking to the response of the laser due to this particular feedback started in 2006. But I want to insist that there's a renewed interest on this particular setup. This came from this group here for the edge-limiting laser, but also there are a lot of activities for vertical cavity surface emitting lasers that appeared quite recently. Okay? All are dealing with square wave generated by this particular setup. And even for micro-ring laser, there is activity using the same type of setup. Okay, so those lasers differ by their design, but the dynamical problem that we are interested in is the same. This is the typical experiment that has been produced by Libre in 2006. So you can see that you can have a square wave that are in antiphase. You can also have fast oscillation that are actually fast relaxation oscillations. Now, those have been discovered by David, but there's no connection with a specific stability or bifurcation diagram. Okay? So one of the goals that we had was to place this in a specific stability diagram and also find a regime that previous work didn't form. So that's, for example, square wave that have a different format. Now, here are the equation, what we call the rate equations. I put them already in dimensionless form. So we have the TE field and we have the TM field. The TE field is the main field in the laser cavity, but because of the polarization rotated feedback, its effect will appear in the evolution equation of the passive field, which is the TM field. Now, there are important aspects of this problem that are worth emphasizing. In this format here, the gain is here n, which is the carrier density for E1, the TE field, but it's much more complex for the passive modes, which is the TM field, where we have a factor k and n minus beta. Okay? Now, k is defined of the ratio of the differential gain coefficients, and it's typically smaller than 1. And beta is a combination of both k, the ratio of differential gains, but also of the cavity constant for the two modes. Okay? So this is what we call the losses, or the relative loss of the passive mode compared to the active mode. Okay? And those modes interact together through the carrier equation here, through the saturation terms here. So they're not independent. So in addition to those parameters here, what is new compared to other studies is that we took into account the detuning. Okay? And why we took into account the detuning? Because Ingo told us to do so. Okay. We review all the previous work that are discussing experimental work with simulation. In all those previous work, it has been assumed that the cavity rate constants are just equal. Okay? It doesn't have to be, but this is a simplification, which implies that the only parameter left that will describe a difference between the two modes are the ratio of the differential gain, usually taken to be 0.8, 0.9. And then you have to compute beta, which is now only depending on k and is typically smaller than 1. It's finite. Now, the interest of those dimensionless equations is not only because they are beautiful, but also because they emphasize some parameters that are either small or large. The experiment are done typically with a large delay. So this tau here is dimensionless, but it's like 1,000. Okay, it's a large value. This T here is the ratio of the laser time constant, and it's also a large parameter, also typically like 1,000. In this particular problem, there are typically two different time scales. One obviously is the one imposed by the delay. So this should be T1 proportional to tau. But there's also a time scale that is proper to the laser problem, so without the feedback, which we call the relaxation oscillation. And that second time scale is proportional to the square root of t. Remember, I said typically tau 1000, capital T 1000, so the square root of 1000 is much less than tau. So we have typically a two-scale problem, but we can use asymptotic methods to construct solution of periodic solution of those equations here. It's not standard because the two limits are singular, but combined with some numerical simulation, you can come with a strategy to actually construct the solution by the method of steps. So each part of the square wave will be constructed knowing what we know from the previous part. Okay. So, yeah.
Assuming that E2 is going to switch on, how can you neglect the feedback in the E1 due to E2?
Well, in the experiment, there is a polarizer that will avoid this feedback. Okay, but it is a good question. Yes, obviously. But that's what one of the first points to check when we did the experiment. Now we can look to the problem where we also have a little bit feedback here. But this is much harder. We'll come back to the macro version. So we can take advantage of those parameters here to do some aggressive asymptotics. I said I will not give you any details, okay? Because this is purely technical, and I will come directly to the answer. This is the stability diagram in terms of the feedback amplitude and the detuning. Okay. There is a stable steady state that loses stability through a Hopf bifurcation to fast relaxation oscillations. So the laser here wins. But there's another Hopf bifurcation line here, which is a bifurcation to stable square wave. Now it is the delay. Our delay that is winning. Okay. You can find asymptotic approximation for those lines, and so this one is exact, but the one here can be very nicely presented by a simple expression. Here are two numerical experiments to find out what we learned from this stability diagram. If I'm right here, in this region here, we should have fast relaxation oscillation. This is what we get. Okay. But as soon as I cross this line here, I should have square wave. And square wave here we have relaxation oscillation, but they are dense. And we have done a lot of numerical simulation to check this diagram. So what this diagram illustrates is that you have actually a competition between two kinds of regimes. One is the fast relaxation oscillations, and then for larger feedback rate, the stable square wave. The effect of the detuning is visible. You know, in this particular range, the diagram here become much closer. The two lines here actually are crossing each other. So if you are in this region here, you may actually see immediately the square. But obviously, the detuning is not a quantity that you can change as easily as for the injection cell. So. Now, pursuing this particular work on square wave, we explored what happened if this parameter k, which measures the difference of gains or even losses between the active and passive modes. When this k comes close to 1, the square waves start to degrade. It exhibits different plateaus, and even the two periodicity disappear, and we get plateaus of very different lengths. So we get asymmetric square wave, different plateau lengths, period has nothing to do anymore with 2 times the delay. We can even have more than 2 plateaus. Very sensible to noise. Okay? So the word here is that when k comes close to 1, the square wave disappear or degrade by the progressively changing in shape. This has not been observed experimentally yet. Okay? But I will come to that particular property at the end. This is the second project that is explored by Lionel Wachter also at UMB. Here is we call an electro-optical oscillator with delayed feedback. The experiment has been done by Laurent Larger. By chance, he discovered this tau periodic solution by just changing one parameter, which is, I think, the feedback rate. You can see that the size of the 2 plateaus can be changed. But nevertheless, the total period remains equal to tau. So there are 2 new features compared to what we know on square wave. One is that you can have tau periodic square wave, not 2 tau. And the second, we can have a plateau length that we can change by changing a control parameter. Now, what is an electro-optical oscillator? That is an interesting setup where you have a part that is optics and part which is electronics. There is a nonlinear modulator. Here we have a Mach-Zehnder modulator, but it can be something different. We have a very long optical line, usually by a fiber of 7 km length. Then we have some filtering that is purely electronics, starting with a photodiode that is re-injected in the Mach-Zehnder. So we have here a closed loop with a delayed feedback. Now, what is particularly interesting with this setup, both for the application but also for the mathematician, is that it exhibits in his model 3 different time scales. Okay? Time scale that can be changed by the experimentalist, depending on his objective. So this is a natural time scale of the nonlinear setup. We have some filtering coming from the photodiodes, which exhibit theta. And of course, we have the delay here coming from fiber that is measured by tau. And you can have different time scale between the 3. And you have a lot of flexibility also to change them, depending on applications. But the new feature is compared to, for example, the old Ikeda problems with the delay, is this filtering. Application, well, application that, for example, have been developed by Laurent Larger group is either to have a nice chaotic output for secure communication application, or contrary, you have here a nice pure microwave signal. It's high spectral purity, for example, for radar applications. And more recently, he has also a proposal for a setup where you can use for the rapid tuning. Okay? And the fact that we can go on those applications because of the flexibility you have in the time constants. Okay, now I come back to my question. Are asymmetric square wave solutions possible with delay-differential equation? Remember, we are motivated by the experiments where we have those asymmetric square waves, different plateau lengths. Here I repeat what I said before, that it's not possible for scalar delay-differential equations. You may observe them as a transient, sometimes even long transient, but at the end, they will always go to a 2T periodic square wave, which is symmetric. But the model equation for the electro-optic oscillators is not scalar. Why? Because we have this integral term corresponding to the filtering. So if you eliminate that integral term by formulating a system of two coupled differential equations, now we have a second order differential equations. Okay. And never mind the f, it's also nonlinearity that involve a cosine function, but there are parameters here which are quite small, and those parameters that are small will be useful for the asymptotic analysis. So here are my equations again, and we are looking for periodic solution of period 1 plus some small corrections. If I take epsilon go to 0, so I kill this term here, we have an equation here that look an equation for a map between x and xt minus 1. Fine, but this is coupled with a differential equation. Okay. So it's much richer than just a map. It is a map coupled with a differential equation. And we can again look for a periodic solution that has different plateau length. Here we have S naught as the plateau length here, and 1 minus S naught as the plateau length of the maximum. The S naught here is the quantity to calculate from the model equations. This line here is a numerical solution. This diagram here that shows the extrema is obtained by the asymptotics. And you can see that for this particular value of beta used for the numerics, it matches very nicely. And again, also for the value of S naught that corresponds to the length of the lowest plateau. Okay. So the asymptotics work very well, even if this extra difficulty coming from the fact that we have a map coupled to a differential equations. But again, the strategy is the same as the previous activity where we solve the problem by steps. In other words, we assume a particular state here, then we can compute the state and so on. Okay. So it's really more a bookkeeping problem where you propose a solution at one stage and then you can compute the solution at the next stage and verify the solution at the next stage. And of course, you have a periodicity condition that is an extra condition. That gives you a set of equations which are transcendental, but you can explore them, and that gives you the bifurcation. The equation ask is what is actually the bifurcation mechanism for the square wave? Those square waves are appearing suddenly in the bifurcation diagram from a limit point, or is there any other bifurcation mechanism? And number two, are you sure that those square waves are the only solution possible in the optoelectronic problem? Question later on recently, and this is the diagram, bifurcation diagram. All those square and triangle are numerical solution, while the line here are obtained by using asymptotics. This basic steady state here has a Hopf bifurcation. This is the first Hopf bifurcation. This is another one. There are many Hopf bifurcations, but they're all leading to unstable solutions. So I only show the one that has the chance to lead to a stable solution. So this is the first one. The first one is a subcritical Hopf bifurcation here. So you have to see a branch here that connects this point here. Okay, an unstable branch connects that point here. An unstable branch connects that point here. And close to here, we have a square wave like that. coming from a Hopf bifurcation. But this is a different story. The second question was, do we have other time periodic regimes? And the answer is yes. We found here a branch of periodic solution, but with a very low frequency. This is the scaling. The scale here is very different from the scale here. Okay. So very low frequency. Okay. Now, those square wave and low frequency solution have been observed in the past in Laurent Larger group, but not for the same value of the parameters. So that new feature, and I insist on that because we have again this competition between two different modes of oscillations, which remind me the competition between a fast relaxation oscillation and the square wave in the two modes feedback problem. So I think I wanted to conclude. Okay, for delay problem, square wave oscillation is usually what happens for large delays. The problem that we are interested in, those square wave solutions appear very often for large delay. The large delay is usually very easily realized in the lab, especially with semiconductor lasers. The two problems that I concentrate were both motivated by experiment. One is a two-mode optical feedback, where we observe a competition for fast relaxation oscillation, which is the signature of the laser, and slower to tau periodic square wave. Okay? We need to have this ratio of the gain coefficient not equal to 1, slightly less than 1, okay? Which is not physically intuitive. We think that if they're closer to 1 or equal to 1, we have a better chance to see square wave. But now, we need to have them sufficiently different, otherwise the square wave disappears. This is what I say here. The square wave degenerates as k comes close to 1. And very recently, I learned that this is the conclusion that came my colleague and his co-workers about finding Robert square wave for VCSELs, because the low dichroism in the square wave is not a favor if you look for square wave for higher pump. And actually, they control the dichroism to get the square wave. So here again, we come to a conclusion that is similar. The two modes need to have sufficiently different aspects, for example, losses, to have a chance to generate square wave. In the electro-optic oscillator, the objective was a little bit different. We wanted to find if asymmetric tau periodic square waves are possible. This was never documented in any literature or math literature that you can get them. And the reason is because from the first time we're looking now for second order differential equations. Well, most of math work is dealing with scalar differential equations. And here, as in the previous plan, we have a competition of square wave oscillation dominated by delay, and here low frequency oscillation. So I think this is features which are typical to square wave or typical to delay equation as soon you go over the scalar differential equation format. You will have different, completely different periodic solution to expect, and you may have now more interesting or richer square wave with different plateau lengths, which can be controlled. Thank you.
So, the question is, I didn't completely understand what determines the duty cycle of this coil.
In the case of Laurent, it's the feedback.
And in your case?
Feedback phase, yeah.
The feedback phase.
Yes. The phi in the Laurent problem.
Why I'm asking, in the case of the two-tone periodic square waves, you certainly have, for simple symmetry reasons, also all the hot harmonics that can occur. So instead of two-tone periodic, you can have then 3 times the frequency, 5 times, and so on. In the case of the tall periodic ones, could you also have more than one switch as long as they are on?
I don't know. We didn't find them numerically. But we didn't push too much. The delay is large, so we didn't push too much the feedback rate. But we explored numerically the problem, and there are a lot of bifurcation to what you said, higher harmonics, but they're all unstable. You can predict them on paper, so we have run a lot of simulation, especially because we had this critic about do you have other stable regimes? But we didn't find as much as we were thinking. And in the old Ikeda problem, you have those harmonics which have been explored numerically and experimentally, but they are mostly unstable. But unstable, what does it mean? It means that maybe you can see them for the time of the experiment, depending on the initial condition.
So, questions?
So, for this case of the two-mode optical feedback, what do you think would happen if instead of a long delay, you will have a short delay, actually as short as the relaxation oscillation frequency? Or?
I don't know. You will lose the square wave, definitively. Yeah. The square wave is because of the delay large. Remember that it's epsilon.
Yeah, absolutely. But okay,
but then you will have, I guess, you have some other solution that will be more harmonic. And that could be possible. Are you thinking about short cavity experiment? You still have you can still do the linear stability analysis and identify candidates for bifurcations. So you're not lost. It's more in terms of the nonlinear problem that it would be harder to do something ethically.
It was a pretty intuition of.
I have to say I'm not completely sure yet what determines this difference in periodicity between the electro-optic oscillator and the oscillator, for example, you presented, between 2 tau or 1 tau. I mean, you mentioned instability for scalar, for scalar delay-differential equation, but that's not the case, right? So, I mean, if you have the two-mode feedback, then you can consider this all as.
Well, the two-mode feedback, you have the laser, the solitary laser, which loves to oscillate the relaxation oscillation modes, but of course damped. Now with the feedback, the damped relaxation oscillation may survive and get sustained. But at the end of the day, the feedback with a large delay will have its last word, provided you have enough feedback rate. So those two different regimes can be expected.
But you won't have the top periodic solution in the two-mode feedback case in the semiconductor layers, will you?
What? No.
No. But,
also, we found some regime where the field can be much larger and nothing related to tau. Okay. Yeah, but there are reasons.
What is the decisive structure in the electro-optic oscillator equations that gives you the one?
It's the Hopf bifurcation analysis. The Hopf bifurcation analysis tells you that you have a frequency that is close to the inverse of 2 tau or 1 tau. And in the case of the electro-optical oscillator, it appears that the Hopf bifurcation that we identify, you can see that the frequency predicts 1 over tau. Okay? So, whereas not a surprise. But in the beginning, it was found experimentally and then numerically without doing this linear stability analysis. Okay? And so, you can also have tau periodic solution in the same device for different parameters.
Okay.
As far as I recall, just to comment on that, because Laurent found it while he was here in Parma, is whether you are at the positive or the negative feedback branch. So that's what determines whether you have tau periodic or two tau periodic solutions.
That's right. Yeah. Well, in that particular case, it's even at the edge.
Yes. One thing I was wondering, you probably showed it, I might have missed it. How does the tau periodic oscillations become then unstable? You said there's a second Hopf bifurcation, so you have a torus breakup, or what would be the mechanism how the tau periodic solutions become unstable?
We didn't find that to become unstable.
You didn't find them to become, so they were always stable?
Yeah. For the range of parameters we were looking. And we really did a lot of numerical work because this was the pertinent question that was asked us. We do back and forth, differential conditions. But for the diagram I have here, it was stable. The problem that we had was that we were not able to see this connected directly to the whole bifurcation. So we did some Bifurcation calculation to discover that we have here a branch of periodic solution here that emerged from the whole bifurcation. But at the time of the Palma conferences, we were still confused. I confess that I believe that this solution here was totally isolated from the steady state. Okay. I was wrong. But we could only demonstrate that by doing this Bifurcation calculation. And this is an important question.
So one thing I noticed that the plateaus of the square waves does that correspond to a stationary state of the system, also unstable maybe?
There are
Or is not?
fixed point of period 2 of the map. Okay, so it's not really a steady state; it's a fixed point of period 2. Okay. And when we construct those plateaus, we do the same approach. We try to find a map, but the map here involves several equations. So what we do is we do a bookkeeping of each part of the square wave that we think are interesting, and then we identify what should be the typical value of what you call the steady value, the typical value of the variable, sometimes with the help of numerals. And then we try the ansatz ethically, okay, to see the consequences. But this kind of game can be quite complex, especially when you have several plateaus. Okay. But we have checked, numerically we have checked everything.
You mentioned earlier the significant noise sensitivity of the square wave solution. Have you found a way to attain a noise stable square wave solution without basically increasing the feedback strength to, let's say, experimentally unrealistic values? Because when I did the simulation, it was very hard to get the square waves. Usually the noise washed them out. I also tried to decrease basically to further damp the relaxation oscillations, but
now I confess that in the lyrics we didn't solve stochastic differential equations. The way we mimic the noise was just by adding a very small term to the field equations. And in this way you can show analytically that the size of the long plateau is related to this amplitude, this small term, by an exponential relation. And that's how we explain the sensitivity. And this we can check numerically, this relation, but this is not stochastic simulations. We wanted just to see how sensitive this very small perturbation, constant perturbation in the field equation will affect the size of the. But I think it's also true if you have put some real noises in the problem.
Questions? I have a couple of questions. One is, do you find also period 2 tau asymmetric solutions, or these asymmetric solutions appear usually only when you have this tau?
No, no. I think it can also appear for 2 tau.
For 2 tau. Because it could appear in any, it's not just some
No.
feature of the tau.
It is the history of the problem, because if Laurent didn't do the experiment by chance, my understanding, the experiment was done during a meeting in Besançon, okay? And we were challenging him about that, and he did the experiment right away, okay? It took us another year to understand why, but we didn't start to think, what about the 2 tau periodic solutions? So we happen that we have this working problem with the tau periodic solution, but I'm sure you can get it
With the 2 tau.
but you need 2 degrees of freedom.
Yeah, you need 2 degrees of freedom, but then you can
Yeah.
get it. Now, the other question is, in the 3 systems that you mentioned in the talk, so first was the Ikeda, then the laser with 2 modes, and then the first and the third, you have a non-linear feedback, while in the second, the feedback is linear. Does this any say qualitative difference in the fact that you have a linear or non-linear feedback, or at the very end for this sort of solutions, it is that's not that important?
I cannot tell. The problem are so rich, already by the format of the laser equations or the optical oscillators, that I don't think the feedback is linear or non-linear. But this, of course, is not the questions. If you take the Kobayashi problem, the traditional problem, and have a non-linear feedback instead of this linear feedback we have, we're going to have a lot of different results.
Yeah,
that's definitely.
To say that when you write down the map, then the delay term is either linear or non-linear.
Everything is going to be changed. But in this particular problem, I don't know. The optoelectronic oscillator is interesting because we can test, where phenomena that are typical to delay equations with an optical system. I mean, you cannot do this with a mechanical system with delay. You cannot do this with the neurons or polarization system. Okay. And that's what Laurent understood quite well. He's mostly interested in engineering application. But when I tried to say that these experiments are valuable to illustrate that you can have square wave with different plateau lengths experimentally, that is important for the delay community, especially mathematicians. I remember some people say, that experiment? So, yes, they're experiments.
Is there any other question? So if not, we thank Thomas again.